Many of the things that happen around us seemingly occur without explanation, like the weights of babies born in a given month. Fascinatingly, underlying many of the observable phenomena we see day to day are statistical and mathematical explanations for why these observations come about. Our research aims to apply this idea to the field of cardiology in the hopes of better understanding heart rhythm disorders known as arrhythmias. In our most recent work, we explored a branch of mathematics known as queuing theory to try and investigate a type of arrhythmia called atrial fibrillation. While the parallels between cues and the heart may not be obvious, it turns out that a common set of mathematical and statistical principles can be applied to model the dynamics of both. To explain, let's first consider some customers waiting in a queue. When we're shopping, we may not pay much attention to how many customers will be waiting in line and how long they need to wait, as this may seem too random to predict. However, using queuing theory, we can quite accurately calculate the average number of customers in the queue, the speed of service, and average wait time. As one can imagine, this can be extremely useful in improving queue flow, as we can then statistically calculate how to serve customers most effectively. While this seems a niche area of mathematics, the applications of queuing theory actually extend far beyond queues at a grocery store, with these principles often being used to model populations in ecology, the spread of disease through a population, and even arrhythmia dynamics. This is because, in essence, these problems are analogous to our shopping example. How? Let's get back to our analogy to elaborate. In our shopping problem, the dynamics of the queue, such as how long on average a customer waits and how many people are in the queue, rely on two fundamental parameters: the rate of arrivals, which we call lambda f, and the rate of departures, which we call lambda d. The arrival rate, or lambda f, is taken by measuring the average time between new customers joining the queue. Of course, we may get some customers who just want to get in and out of the store quickly, so will arrive at the queue at a faster rate compared to the shoppers who wander slowly down every aisle. To get an accurate average arrival rate, even if individually customers arrive in the queue at random times, we simply construct a distribution using the inter-arrival times for all customers to get an average rate for lambda f. A similar idea is applied to obtain lambda d, or the departure rate. If we take a measurement of the time it takes for customers to be served and leave the queue, we can construct a distribution of departure times to give us lambda d. These queuing systems are also called birth-death processes, as the rate of arrivals, lambda f, can analogously describe the rate of births in any given system, while the departure rate describes how quickly entities die. This terminology makes more sense if we're considering populations in nature. For example, studying how the births and deaths of frogs influences the overall population of frogs in a pond. Just by knowing the two parameters lambda f and lambda d, we can thus model things like the population size of any species, which intuitively relies on the ratio of the arrival rate versus departure rate, and other interesting phenomena, such as whether a species is likely to face extinction. On application, there are several different types of birth-death models, and using queuing theory notation, these can differ depending on how the rate of arrivals, lambda f, and rate of departures, lambda d, come about, as well as the number of servers. To illustrate, consider the scenario where entities are arriving and departing a system completely at random, meaning arrival and departure times are statistically independent. With reference to our shopping example, this would mean that the time it takes one customer to join the queue has absolutely no influence on how long it takes another customer to join the queue, and likewise with the time of their departure. If this is the case, then we can say the rate of arrivals and departures has no memory, which is also known as the memoryless or Markovian property. Furthermore, if there was only one cash register or server, as shown in the example here, then the birth-death queuing process can be modelled using an MM1 model, where the M's represent the Markovian arrivals and departures, and the 1 represents the number of servers. If we instead had 3 servers, then this would be an MM3 model, sometimes referred to as an MMC model in the general case. In our research of atrial fibrillation, an arrhythmia typically characterized by disorganized electrical activity, we observed that a similar birth-death framework could be applied. When we study things like the times between new electrical waves forming and how long they took to be destroyed, we found that with analogy to the shopping problem, arrival and departure times of these waves could also effectively be modelled as statistically independent, hence exhibiting the memoryless or Markovian property. This applied to the different types of electrical waves, like wavelets, which are fractionated segments of the electrical excitation wavefront, as well as reentrant circuits, which are spiral-shaped waves that spin in on themselves. Given the effectively Markovian nature of arrivals and departures, we hypothesized that a birth-death model with random arrivals and departures, like the infinity model, could accurately summarize the population dynamics of these electrical waves in atrial fibrillation. Note that the infinity in this case refers to the fact that all waves are immediately able to be destroyed, which is analogous to the scenario where there are infinitely many cash registers or servers available, allowing a customer in the queue to be served immediately. Our research findings show that not only does the infinity model summarize wave population dynamics, it also presents governing equations that may be useful for further understanding AF, such as why we may see certain wave phenomena more commonly than others. These equations seem to apply over various model systems such as humans, sheep, rats, and computer simulations, as well as across data acquired from various methods such as basket and HD grid catheters and optical mapping, suggesting robustness. Furthermore, these birth-death models seem to provide some insight into how AF may terminate, which may perhaps help us understand how to advance therapies for the treatment of atrial fibrillation in the future. To read more about our work, head to Frontiers in Physiology for an open access manuscript on our latest findings.